Alright, hey guys, Mr. F here. I just wanted to give you an update video on the practice problems I had you look at. These were the problems from the worksheet, exercise 2, 3, 4, 5, and 6. So I know we already did number 2 in our notes on the YouTube channel, but I want you guys to remember the impulse equation. Impulse equation is force times time equals mass times velocity. And remember, this velocity right here is really a delta V. Now sometimes the delta V will be the difference in velocity when one of your velocities is already 0. The number you get will just be the answer, because anything minus 0 is itself. I know it's kind of confusing right now, but just remember, you'll probably see that in just a second. So remembering both of these equations. So just a quick refresher on number 2. Auto companies frequently use safety of automobiles by putting them through crash tests to observe the integrity of the passenger compartment. If a 1,000-kilogram car, so we have a mass of 1,000 kilograms, is sent towards a cement wall with a speed of 14 meters per second, and the impact brings it to a stop. A stop implies 0 meters per second, and we could see here that this would be our initial velocity and that is our final velocity. Okay, just adjust this sharpness here. You guys can tell me if it's getting better or worse. And you're probably saying, whoa, whoa, Mr. F, getting worse, getting a lot worse. And we're going to work with that one right there. So back to this, and then we have a time of 8.00 times 10 to the negative 2 seconds. But this we know in standard notation is really just 0.08 seconds because we moved that decimal 2 times over. Alright, and we want to find the force. So using the equation, Ft equals mv, and we know that v is really a delta v, which is equal to v final minus v initial, always, always, always final minus the initial. We can plug in what we have. F equals 0.08. M would be 1,000. And v in this case, the final minus the initial, would be 0 minus 14. F times 0.08 equals 1,000 times negative 14. F times 0.08 equals negative 14,000. Take our handy dandy calculator here, and we will next divide 0.08 on both sides. So we get negative 14,000 divided by 0.08, negative 175,000. F equals negative 175,000, and don't forget your units. Those are newtons. Let me see if I could darken this calculator up a little bit for you guys. How's that? A little bit better. All right. So that's number 2. Move on to number 3. Questions? Questions? Anybody? Anybody? Make sure you send your emails to me. Okay? Number 3, Rhonda, who has a mass of 60 kilograms, is riding at 25 meters per second. So we have a mass, 60 kg. We have a velocity, we're not quite sure if it's an initial or final, 25 meters per second. In her sports car, when she must suddenly slam on the brakes, that's the brakes, to avoid hitting a dog crossing the road. She is wearing her seatbelt, which brings her body to a stop in 0.4. Okay, so her body comes to a stop, which means our other velocity is 0 meters per second. So we now have a final and an initial, and we also had the time aspect of it. The time was 0.4 seconds. A, what average force did the seatbelt exert on her? So we're going to look for force. That's our first part. So in A, let's solve the standard impulse equation. F times 0.4, good. Mass is 60, very good guys. and our change in velocity goes from 0 minus 25. Now notice, when we're changing our velocity, we're going from a speed we're traveling at to a stop, from a speed to a stop. Now this isn't always the case, but I need you to understand these forces come out negative. Okay, that's because the force is acting, it's stopping us, it's slowing us, it's acting in the opposite direction as travel. So if we're here, right, that's some guys here, and he is moving in this direction, in order to stop him, the force needs to act in the opposite direction, and that's why it is negative, because our direction is positive. So going through here, we find that we get F times 0.4, 60 times 25 comes out to be negative 1500. We divide by the 0.4, and we get a force as equaling negative 3750 newtons. Okay. All right, so that was A. Let's look at B. B says if she had not been wearing a seatbelt and the windshield had stopped her head in that given amount of time, so we have a new time here, 1 times 10 to the negative third, what was the average force? All right, back when I first started to introduce this to you, I wanted you to think of a bungee jumper. That's the bungee, and someone with a chain jumping from, a bridge. So this guy, and then you got this guy. Now when this guy jumps, he's going to fall, and then all of a sudden, that chain might actually just cut him in half, because there's no absorption. The time here is very small, okay? But this guy, on the other hand, this bungee is going to stretch all the way down. And he'll be just fine, because the time here is very large. And what do I mean by large and small? Well, it's the contact time. It's the absorption. So here, this bungee is going to absorb a lot. And think from the time of 0.0 to its maximum stretch, there's a lot of time going on there. Here, from 0.0 to maximum stretch, it's a very small amount of time. So what can you think about forces? Who's going to feel the greater force? That guy? Or this guy? And the answer is this guy. He's going to feel a far bigger force than this guy, who's going to have a smaller force. So think about this. A smaller time yields a larger force, while a larger time yields a smaller force. Think about boxers and why they wear, right? That's a boxing glove. Think about why they wear boxing gloves. It's to compress all of this, right? If you compress that, when you get hit, the contact time is longer. And if you have a longer contact time, you have a smaller force. All right, so let's get back to this problem here and what we're looking at. We see that we still have the mass, we still have the velocities, but we have a new time in this case. So let's plug it into our equation. Ft equals m delta v f times. This time goes to 0.001. 0.001 equals m 60 times 0 minus 25. So we know from the last problem that we just did, right, up here, 60 times negative 25 is 1,500, so I'm just going to plug that in here. 60 times negative 25 is negative 1,500, and then let's divide. And we find the force here, and think about this. The smaller the time, right, we decreased our time substantially, so we should increase from our original force substantially. And in fact, we find that we do. We go from negative 3750 newtons to negative 150,000 newtons. This is why you wear seatbelts. You want to increase your time. By increasing your time, you decrease the force. That is what impulse is. That's the whole point of impulse. Alright guys, you're doing good. I know you got this. You can't see the thumbs up, so I'm going to give you a sideways thumbs up. Alright, let's keep moving on. And we're going to take a look at number 4. Alright, if 270 million people, so right off the bat we got 270 million people in the United States jumped up in the air simultaneously, pushing off from the ground with an average force of 800 newtons, each for a time of 0.01 seconds. What would happen to the Earth? The Earth has a mass. That's the mass we're going to use. 5.98 times 10 to the 24th kilograms. We want to find out what would happen to the Earth. Okay, so essentially what we're looking for is the delta V. Now, in this case, we're only going to look for one velocity. Now, I know delta V usually means final minus initial, and that's two velocities. But V final minus V initial. If we're assuming that the Earth is still to begin with, that's 0. So when we solve for a V, we're really going to get the V final. Okay? So hopefully you kind of see what I'm talking about there. So we're only looking for one V, not two, just one. So let's just plug this into our handy dandy equation. Ft equals m delta V, or just V because we know 1 is 0. 800 times a time of 0.1 equals the mass, 5.98 times 10 to the 24th, times our V. Alright, so let's do the math. 800 times 0.1 is 80. And then 5.98 times 10 to the 24th times V. We need to divide. And this one is going to be plugged into your scientific calculator. So let me just show you. Right, so we're going to take 80 and we're going to divide it. Let's see if I can turn on the light for you guys. Hopefully it doesn't blind you. Oh, that's a lot better. 80 divided by parentheses 5.98 second comma. That gives us the little e for exponential. And then we're just going to put in our 24. And we get a velocity equaling 1.34 times 10 to the negative 23rd meters per second. Now, you need to understand this is for just one person. But we have 270 million people. So we need to multiply this value by 270 million people to get our final answer. So we're going to take it in times, 270, 1, 2, 3, 4, 5, 6. And we get 3.61 times 10 to the negative 15th meters per second. This is our V, okay, our velocity. That's how much the Earth would move, and as you can see by this negative 15 right here, it is inconsequential. It's not even going to move that much. Because think about it, when you transfer your momentum to the Earth's mass is extremely larger than you. It's like the bug in the windshield, right? The bug's going to hit the windshield and die, but the windshield doesn't feel anything, the car doesn't feel anything because of the mass differences. So, hopefully that helped you with number 4. It's kind of tricky with the scientific notation. We're almost there. Let's move on to number 5. Looking at number 5, we have in Sharky's Billiard Academy, Maurice is waiting to make his last shot. He notices the cue ball is lined up for a perfect head-on collision as shown. Each of the balls have a mass of 0.08 kilograms. So we have some masses, 0.08 kg. Cue ball comes to a complete stop upon making contact, so all of its momentum becomes transferred. Suppose Maurice hits the cue ball by exerting a force of, so we have a force of 180 newtons, and we have a time of 5 times 10 to the negative third seconds. So, remember, if we put this back into standard notation, that's 0.005 seconds, because we're going to move that over 1, 2, 3 times. And knocks it into the 8 ball. Calculate the resulting velocity. So we want to find that velocity. And again, here we go. Same idea. This is a delta v, but you already know one of the v's is 0. So when you find the velocity, that's your answer. Plug it into our handy dandy equation. Ft equals m delta v, or just v, 180 times 0.005 equals 0.08 times v. 180 times 0.005 equals 0.9. And what do we do, class? You got it. You divide. Good job. And we find out that v equals 11.25 meters per second. Always remember your units. Always. Point at you guys. Point at you. Alright, let's see. And our last one, number 6, our last one for the day. During an autumn storm, a 0.012 kilogram, so we have a mass, 0.012 kilogram. Hailstone traveling at 20 meters per second. We have a velocity, 20 meters per second. Made a 0.2 centimeter deep dent. Okay, so we have a displacement, or an x value, of 0.2 centimeters, and we know we don't like centimeters, so that would be 0.002 meters in Darnell's new car. What average force did the car exert to stop? Okay, so we have a final velocity of 0, initial velocity, to stop that hailstone, and we want to look for the force. Alright, let's take a little look-see here. What do we do first? Well, if we wanted to plug in our equation, I'm sorry, you guys should have told me. I didn't show you half the stuff. Come on, guys. You got to be on this. Excuse me. So, Ft equals m delta v. We have a force. We do not have a force. We have a time, though. We do not have a time. So we do not have a force or a time. That's not cool. It's not good at all. We do have a mass, though, 0.012. And we have a velocity. That velocity just goes down from 0 to 20. So, how are we going to find the force and the time? Well, the force is what it's asking. So we can't find that. But we could certainly find the time. So how are we going to find time? Well, think back. These equations never go away, guys. These equations never go away. In fact, let me see if I can bring this up for you on my pictures. You guys remember all these equations, right? Let's see if it'll actually focus. There we go. So, these equations never ever go away. So the equation that we're going to be using to actually help us and find time is this equation right here. We have a velocity. We have a displacement. Let's use that to find time. Alright. So, x equals x equals vt. So we have an x. The x is 0.002 meters. Alright, guys? The v is 20 meters per second, and the t is what we're looking for. So we now know that the time comes out to be 0.0001 seconds. And now we could use this to plug back in. So F times 0.001 equals 0.012 times negative 20. F times 0.001 equals negative 0.24. Let's divide. F equals 240 newtons. So, did I do this right, guys? I'm looking at my answer key. Give me 1 second. Let me just double check this one. Yeah. Oh, no, I didn't. Look at 3 zeros. I forgot a 0 here. Guys should have caught me. You guys are better than that, so it's just going to tack another 0 onto there. So, 2400 newtons. That is our final answer. Alright, guys. Goodness. Well, I'm hoping this helped for you guys. I'm going to put this on the YouTube, and hopefully this helps. You can go over this as many times as you want. Ask me any questions. And I will sign off. Take this camera quick. And I will sign off, and I will say, hey guys, hopefully everything's good. See you guys. Bye.